we finished off last time, I think, with, we were doing rod on rails problems, right? I think we did 30.11 on page 179. So let's go ahead and go to page 179 in the workbook and kind of catch up there. So let me start with the screen share. Whoops, wrong one. I think it was, yeah. So just a reminder, yeah, okay. So that's where we're at. I know what I want to do. I want to write something on the board. Sorry, I'm a little all over the place here. Give me just a second. Okay. Last time we started talking about EMF, induced EMF. So let me give you a very brief reminder. If you have a loop of wire and there's some area in that loop and there's some B field floating through here, let's say this is the B field. You could slice this thing up into little chunks and get an area vector for that a small amount of area. And you could do a dot product and integrate over all these little chunks and add up to get the magnetic flux. For a lot of problems, B external is uniform. Maybe you put the experiment inside of a Helmholtz coil and you know what I'm talking about? B was uniform inside of there. So many cases, this is true. And then the integral simplifies to this. It would be B times the area of the loop times cosine of the angle. You wouldn't have to worry about changing angles and such, right? If it's uniform, that's done. So then we also learned that EMF is minus N d phi dt. So if you want to find the voltage, electromotive force or voltage, it turns out there's an analogy with mechanics where voltage and force are equivalent in this analogy. We'll learn more about that in another chapter. But electromotive force, voltage, E, same thing. This can be described by a change in magnetic flux per unit time and then some loops. The minus sign is indicative. The voltage does not oppose the field necessarily. It opposes the change in flux. So it tries to keep the magnetic flux the way it used to be, whether that's adding more of the field that was lost or opposing a field that was added to it. So sometimes it opposes the field, sometimes it opposes the loss of the field by trying to put the same field back. Finally, we did one other thing. Don't get too emotional. That would be BL V. And I think I put a perpendicular. You need to put it on here or there. The idea is you take the component of B perpendicular to a rod that is moving in the presence of a magnetic field. If the rod has this length and this speed and this amount of magnetic field perpendicular to the motion, we know the electrons in the rod are going to end up moving around and effectively create a voltage in the moving rod. Or excuse me, not in the rod. I should have said voltage across that rod. So a moving rod in a magnetic field is basically a battery. Any questions about the review?
I don't have a question about the review, but or maybe this is a question about the review.
Yeah, go for it.
There, okay, maybe I'm just thinking about this wrong. Is there direction in voltage? There is, right? You can.
Yeah, so we actually say, so I don't know if you remember, a lot of times I was really loosey-goosey and we said potential difference, right?
Right, potential, yeah.
And so we usually say this would be a potential difference of E.
Right.
Now, the directionality of it is basically saying which side of the rod is at higher potential.
Okay, okay.
And so this is actually a very good question to clarify. This means the difference of voltage between the two ends of the rods.
Okay.
and which side would be positive or negative, the term that you usually use as a scientist, you say, which way is it biased? So that just means which side is the high polarity, or which side is positive and which side is negative, or which is high and which is low.
Okay.
So a lot of times, let's say this was a battery and the red tip is the positive terminal and this white area would be negative. This, you could say, which way do you want to apply the bias? And then if you flip it, you say you reverse biased it. So that's the terminology sometimes you may see on the internet if you're reading. Is that good?
Yep. Thank you.
Yeah. Yeah. Okay. Other questions? That was a good one. So this is actually the potential difference across the rod, or the potential difference across that loop. Yeah. Okay. It's a little bit weird because when you think about it, if you just have a loop of wire, it's not like there's a battery in it. So that's, yeah, it's more on that later. All right. Okay. Let's go ahead and look at those problems again now. So I think we did this type of problem right here. This is called the rod on rails problem. Let's step it up a little bit and try this one. So now I know you, in theory, know how to do this, but there's a few subtle differences between this problem and the last problem. So I'm going to draw this up and then we can talk about it. If you don't want to listen to me, you try and do it and try the problem, then check the answer. Try it, then check the answer. Okay. So if you think you know what you're doing, don't listen to me. I'm just going to draw this and we'll work together, those of you that want to. Okay. Let me try something else too. I don't know if this, well, you guys have Discord groups you can go to if you need to. But yeah, so if you want to work on the Discord on the side because you think you know it all, I totally get that, because you might. So I'm just going to draw this up again. I'll put that screen share up again. Sorry. A little off tonight here. All right, let's just go this way. Sorry. Okay, so we've got a loop here. This is 30.12. There's a wire. Okay. There's a rod here. Okay. Is it released from rest? Okay, in part C, it says released from rest, by the way. I just read ahead. Looks like we got a field out of the page. Okay, and then we got an I hat to the right, J hat up. All right, that'll be convenient so we can communicate better. If I hat is right, that means K hat is out of the page. Always check that. Okay, so the givens, M, G, L, R, and B external equals B in terms of magnitude are all given. We're using the case 1 figure. Okay, got it. All right. And then, so hopefully, whoops. So we got that picture. Just getting the same picture open in my workbook. Okay. And so in this case, what direction is induced current in the rod? Let's see if you can remember. Anybody unmute and tell me.
Counterclockwise.
So let me see. As you go down, oh, Tom, do you want to try and explain your reasoning so we can understand it?
Yeah, let's see if it's right. As it falls down, there are less dots. So three more, or I don't know, a couple more dots are generated to maintain balance. And if a dot shows up, that means a current flowed to the counterclockwise.
Correct. Good reasoning. Nice job. So now we know which way current flows. Sweet. So let's keep going. Somebody else. What direction is the magnetic force on the falling rod?
Is it upward?
Let's see. Oh, wait. What's your reasoning?
That was my reasoning.
Yes. I goes to B, goes to up. Let's check. Is it magnetic braking or magnetic make you go faster? It's opposing the motion. That sounds good. It should be magnetic braking, not magnetic make you go faster. Here's a trick. Check this out. While not always true, you have a cross product in this magnetic force, right? Magnetic forces should never change your speed because they're perpendicular to your motion. They can only change your direction of motion. Maybe you've heard it said that magnetic forces do no work. Remember what work means. Work is the change in kinetic energy, which relates to 1/2 mv final squared minus 1/2 mv initial squared. If you've heard that phrase, whoops, right there. Think about it. Magnetic forces should, in theory, not change your velocity. I know some of your coders are thinking, wait, it did. Double check. We'll look at that later. Do some print statements. Maybe there's a plus equals error. But the fact is, in reality, magnetic forces are perpendicular to the motion of a charge. So now, in this case, you might be saying, wait, if it's not doing any work, is it going to slow you down? This case, it's the magnetic force on a rod, not on a moving charge. So they're a little bit different, but all right. I'm probably just confusing you. So let's move on. Magnetic forces on a moving charge should do no work. That's what I was trying to say. In this case, it's perpendicular to the motion, and that's what this is a little bit different because it's L cross B, right? So it's not necessarily, right? I'll leave it at that. The rod is moving this way, the current's going that way, and so you could get a force that does work on a rod. All right. So next, determine the terminal velocity. Determine the terminal velocity. How would we figure that out? What does anybody know about terminal velocity? Anything?
It's where your
acceleration is 0.
Yeah.
Okay, I'll buy that. So in this case, if acceleration is 0, what's something we might try? Yeah, drag equals gravity. So that's a free body diagram, right? Well, all right. So let's see if this makes sense. Initially, when you release this thing from rest, all of you were good there. So in this case, when you initially release it from rest, how fast is it moving? Not fast. So how much is the flux going to change? Not much. If the flux isn't changing that much per unit time, you don't have much voltage. So you don't have much current. So you don't have much magnetic force. You're still accelerating. At some point, this gets changing so fast, eventually, boom, this magnetic force gets so large, it can actually counteract the effects of gravity. Did that make any sense, maybe? Hopefully.
Yeah.
All right, so there are two different ways to figure out this magnetic force. The equation for the magnetic force is ILB sine of what angle? What is the angle between the current and the magnetic field at this moment?
Is it 90?
90. So what's sine of 90?
14.
Good.
No.
Perfect. All right. And so hopefully they're not always this easy, but in this particular case, we could just say force equals ILB. How do I get the current? Where's the battery? There is no battery. I'm so confused. Help me out.
You have to use voltage
Mm-hmm.
and
What voltage?
resistance.
What would you use for voltage?
That exactly. You have to use that equation to solve for it, right? The E equals negative N.
Oh, you want to go that way? All right.
I'm just taking
That
shots
is-
in the dark here.
That's totally valid. It turns out
Okay.
I was going to do it both ways.
Oh, okay.
So one way to do it is to say E equals B L V. The other
Okay.
way to do it is it's minus N d phi dt, and they are the same. And I wanted to show you that. So let's start with what you chose, Nick, this one. I'm going to start with the easy part. N equals 1. Got it. One loop. Now you do the rest. How do I get the magnetic flux? Do you remember any equations for the magnetic flux? Anybody?
B dot dA.
Yeah, and then now in this case, it's B is uniform, so I don't need the integral, right? So it's B dot A. You see the subtle difference there that I said? I'm taking the whole area of the loop because B is uniform over the entire loop. Is that good, Tom?
Yeah.
Right on.
Really
Now,
quick,
wait.
not to
Oh.
derail you, but do we typically have area where we have to take chunks of area where they're not?
Oh, this is how we do it all the time.
Oh, okay. All right, cool.
Yeah, this is more likely than the other way. If we were going to do the other way, I would make you code it because it's impossible without coding it.
I was thinking of some weird situation with like a bowl of charge, and you move down the bowl, it has a different
That's
radius.
exactly what I was thinking too.
Yeah. And so you could do all of those really easily with coding. Do you agree? Remember the electric potential where you just split it up into grids and you did little plates? You just get the B at the center of each plate, dot it with the area vector at the center, and then it's done. So it would be really easy in coding, nearly impossible on paper. Okay. All right. Did I address that? Is that good for you guys? I didn't know if I...
I'm good.
Yeah.
Okay, cool. Yeah. All right. Now, what's BA here? Is it Baracus? You guys probably don't even know that reference.
Badass.
Yeah. B.A. Baracus was Mr. T in 18 back in the day. B.A. Baracus. So anyways, what's B dot A in this particular case? Which way does A point?
They're the same direction.
Area points perpendicular to the loop. Think about this. This is my loop. That's the direction perpendicular to the loop. That happens to be the B field too. So what happens to the dot product and the vector symbols here?
There's 0.
All right. There we go. So we got B. What's the area of the loop? This is where it gets sneaky. How do you figure out the area of a rectangle?
Length times width.
Do we know the length or the width or the height or whatever? What do we know?
Don't we all only know the length?
You're right. So let's make up a variable for the other name. What's a good name for this distance right here?
Why?
Why not? Okay. So what would be the area then?
L times Y.
Ly. Now remind me here, and I've been picking on Nick a little bit, so let's go to somebody else. Somebody other than Nick. I argue we could simplify this. In fact, not everything in here is changing. What can we pull out?
Everything but the Y.
Exactly. Freaking dog. Just a second. God, so loud. All right. BL. What's left? dy dt. Oh. Okay. Wait a minute. What's a good name for dy dt?
Velocity.
Same shit. Do you agree that this is that? The minus sign relates to Nick's question earlier about what about bias and direction?
Yeah,
we know that this gives you the magnitude of it. The minus sign, we already accounted for that because we know the current is going to create a situation which opposes the change. That's what the minus sign stands for. So it's actually a little bit easier to go right to this.
So really quick question then. If we use the other one, how do we get the minus sign into it?
You just take the absolute value of it and just say, the idea is this gives you the potential difference across the rod. And then you use our knowledge of the current direction from right-hand rules.
Oh, okay, gotcha. Okay.
So this minus sign just helps us figure out what this is. Now you could get technical here and use this, right? dy dt, isn't that velocity in the y direction?
Yeah, exactly. Yeah.
And so wait a minute, isn't velocity in the y direction a negative number? Ding, ding, ding.
There we go.
See what I'm saying? And so this gives you the magnitude there. And so now in general, what do? I give a rat's ass about this minus sign if I know how to think through it. So the minus sign is great if you're doing a code and you have to get it right. However, in practice, it's usually easier just to say, well, I know the size of it is, just ignore the minus sign, get the size of it, and then think about all this other stuff. That said, you should leave the minus sign in, strictly speaking, and then understand it. So just kind of pointing this out here, because Vy in this case is negative, we actually get the same answer because this was speed and this was velocity. And it's a negative velocity, so they match up. All right, so far so good. And now we see basically this is a great way to understand where this equation comes from. I'm going to erase it all now, unless there's any going once, twice. Sold. All right, so we know this is true. Now what? What are we supposed to get?
Velocity.
Aha, that's convenient because it's right in there. And so now we see the unknown that we were dealing with happens to be the unknown that we were looking for. All right, so how do I get that into here? Remind me.
We know that the current I is equal to the voltage over resistance.
Got it.
And so you plug all that stuff in for voltage.
Mm-hmm. B squared L squared V divided by R. Is that right? I think so.
That's what I got.
How do I get V though?
You mind if I back you up just a little bit?
Yeah.
Where did the E over R, where did you get that? Yeah.
Voltage over resistance.
Oh, okay. Got it.
Yep.
Yes.
So this R is the resistance. Yep. Okay. Next. Is that good? How do I get, I don't know what this is. Oh, I'm so stuck.
Sure we do.
How do we do it?
We know that for it to be, I guess, not accelerating, then that force needs to equal mg.
If A equals 0, ding equals ding. Okay. And then known. Got V terminal. So far, so good?
What was the step between the E over R and all the squared stuff?
Oh, I took this and shoved it into there. I took this and shoved it into there. Is that what you needed?
Oh, okay. Yeah, I got you.
Cool. And then I said, well, this has to equal that, and we're good to go. I'm going to do this one more time, though. What if A is not equal to 0? Wouldn't it be accelerating downwards? Right? Let's say it's just early on and it hasn't hit terminal velocity. Wouldn't this thing be accelerating downwards? How would that change this equation? It wouldn't change this. But I couldn't just say these two are equal.
You would say that F of B is equal to mass times the acceleration, right?
Not quite. You're on the right track, though. Yeah, something like that.
Would you just write it as an inequality?
Well, no. What? Let's say I was Newton and I wanted a law, and it happened to be the second one. That's a very clear hint. What do you do with a free body diagram? Always?
Summation of forces.
Yeah, tell it to me.
Yeah, you could do the magnetic force minus the force of gravity equals mass acceleration.
Nope.
No? Wait.
Which two should have the same sign?
Oh, yeah. My bad.
Yeah, this is
same
110,
sign.
baby.
Yeah.
Physics 110. Oh, yeah. mg minus force B equals mass times acceleration, right? Think about it. If you wanted to put a coordinate system on this one, you could do that, but then you could, so if you wanted to do that coordinate, you'd say FB minus mg equals m times what, Phil? If this was my coordinate system,
Yeah, that'd be negative A.
that would be negative A, which ends up giving me this equation when I multiply
Yeah,
everything by negative 1. You know what I'm saying?
Yeah.
So
my
here
bad.
A was the magnitude and this was the direction. Elevator problems. Oh, yeah. All right. So, and at this point, how could you get the velocity as a function of time? Old school. You guys remember this?
Is there like an integration or a derivative or something we're gonna have to take here? I'm
Getting warmer. What do you have to do before you integrate? Blankety blank before you integrate.
Get it by itself.
Separate before you integrate. Separation of variables. All right, whatever. Let's check it out. I don't know if any of this is making any sense to you guys, but take a look. Don't you get, I'm going to divide by m. Why? Because it's easier. So I divided by m. Now I got this equation. So I get g g minus this junk, b squared L squared over Mr. G. Oh, wait, Mr. We're not Mr. G yet. Mr. Let's check. B squared L squared V over R divided by M. Equals dV dt. Clearly, you could solve this with coding, but you could also solve this one analytically, which allows you to check your code, which is a good skill to know. How do you separate this? Remind me. What do I put where? I'll just get this out of here so it's easier to read. How do I separate this? Remind me.
You're going to get the velocity on the right side.
How do I do that?
Carefully.
Wise choice of words. What
Add
else?
that chunk.
Nope.
Oh, right.
Yeah. How about we start with something easier? how do I get T on the other side?
Oh, right. Yeah, you just got to multiply both sides over by T first.
And when you do that, you have to put parentheses around this. And that gets rid of the T. Once you do that, now tell me how you get the V on the other side.
Divide by the parentheses.
Divide. So you can't just add, because when you add, you still haven't separated the T out. So that would have worked, except you can't separate it. So then you get this crap over here. Blah, 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 blah. And so we get something that looks like dt equals, it sounds like dt equals part G of this question. And it's solved in the workbook. You could do it later. Got it? So I kind of guided you through that to remind you, but part G will walk you through it. So you could try this later. I glossed over a lot, erased a lot, tried to make kind of give you an idea, but force you to do the details at home. So part G, I think, will help you do all this again. So I'm going to pause there. Questions? It's just math, not physics. All right? Yep. How we doing? Medium? It's probably been a while, but I'll let you guys work through that one. I got to say, even though you, whoops. Oh, geez. So here it is. Velocity is a function of time. We just did that part, basically. The math on this, you may be saying, this actually relates to those RC transient circuits, right? I don't know if you recognize it. It's the same equation as the RC transients, just it looks a little uglier. Same equation. Now, why would we care about that? Haven't we already? Oh, it's because it's in the next frickin' chapter too, when we do RL transients. So this is a good reminder of all that math. So definitely do that part, okay? All right. So you're definitely going to want to do this math because it will help us get comfortable with the math required with RL transients in the next chapter. And that'll be your third time you hit it. RC, this problem, RL, and then you're really good at this problem happens in a number of situations in the real world all the time. Exponential decay or asymptotic approach to a value. Next, let me just check something really quick. All right. Let me give you some highlights here. I appreciate you guys toughing it out. This is kind of a dry class sometimes, but this is some of my favorite stuff. You can do this problem. This is no joke, and it will surprise you. Okay. Yeah, right? Oh my gosh. I wish. Okay, so this one is tricky. You should do it and enjoy it. Here's your tacos and your frogs. That's a variation. These are all the different ways I might put this on a quiz or a final exam, okay? So there's the rod on rails type problem. There's this particular problem here where it's a loop of wire near a straight wire. One of the wires creates a magnetic field. The loop then has a magnetic flux. And then you can pull the loop to the right or to the left or up or down and see which way it will get an induced voltage and a current flowing. What happens to that current over time? I'm telling you, this is a really good one. Part D is particularly nasty, but the first parts are all not too bad. This is a different style. I show you some plots, and this is a good conceptual question. This one is a classic. It's in every physics book ever. So it turns out, think about this, when you swing a rod, this gets tricky. So let's talk about this one, 30.15 briefly. All right. I don't want to spend all day on it because, unfortunately, we have to get to inductors in the last half of this class, I think. So I just want to point something out here. I'm going to walk you through this because this derivation is particularly confusing. Was this X's? This is 30.15. All my X's are B external. They're not from Texas. It's a very different situation. Okay, so here we have a rod It's swinging about this pivot point. When it swings, it's going around this way. Do you think there will be an induced voltage across the length of the rod? Yes or no? If so, which end would be positive or negative? Forget the questions that are written there. Let's just focus on this first, and then we'll talk about the question. If you look at this conceptually, is this a rod moving in a magnetic field? Yes. Is the B field perpendicular to the rod's motion? Yes. Right? The motion of the rod is this way. The B field's into the plane. The motion of the rod is in the plane. Clearly, it's perpendicular. There must be some motional EMF. Think, if you put an electron here, electrons are usually the objects free to move in a rod. Which way would that electron want to go? Towards the center or towards the end? Towards the top, towards the bottom? What? Which way
Towards
is that?
the end?
Let's think. Yeah. So Trey, walk us through it. Which way is this electron moving when it's inside the rod?
So it would be moving up and to the left.
Correct. That is the direction of the motion. How could I find that value for the velocity or the speed?
Rotational kinematics.
Yeah. It's not your omega, it's not your omega, it's
R
R
omega.
omega.
R omega. Okay. So this is the worst class ever. But there we go. Gosh, it's so dumb. I don't know if these rhymes help, but whatever. So yeah. Okay. So in this case, Trey, I think he said the electron should end up here. I have no idea. Everybody, is that what you said, Trey?
Yes.
Okay, so let's check it out, everybody. What do you think? V goes to B. Shouldn't it be towards this end?
An electron.
Oh, that sneaky electron. Because it's a negative, you got to flip the right-hand rule. So Trey is correct. So based off that, do you agree that this end of the rod would be left positive? Now, here's where it gets weird. Do you think all pieces of the rod move the same speed?
No.
No, they all have the same rotation rate. They all have the same omega, but they all have different R's. So that leads you into this question. If you just did this rod here, you could look at one little segment. So there wouldn't be a voltage across here. There'd be a DE across this little section, which would relate to B, L, V, which in this case is the length would be, how much length does this have? What's a good name for this length? It's not the length of the rod, it's the length of the segment, which is?
Little r?
Not quite.
Big R.
Yell.
No, it's not big R. This distance is R. What's a good name for this distance?
Oh,
R
dr. Sorry, I
little?
thought you were talking about the distance to the chunk.
Yeah, okay, so that would be right here. That's the velocity. And then the length of this particular chunk would be dr. And so when you slap that in an integral, done, right? Can you guys think of any metal rods that move in circular path in an in a magnetic field on a daily basis, all over the world, all the time?
A compass?
Interesting. Yeah. Now a compass would be a challenging one because it tends to align with the field and stay there. So it tends not to be swinging around as much. How about something that's swinging around all the time? Maybe something that's attached to a motor.
Helicopter.
What's that?
Helicopter.
Helicopter blades. So you could actually figure out the voltage between one end of the helicopter blade and the other and see if it's enough to cause problems with the electronics in a sensitive system. So yeah, I think it's a couple millivolts because remember B field for the Earth is about half a Gauss if it's all perpendicular. But usually the Earth's field is not perpendicular to the helicopter blades. It's usually, depending on your latitude, only a component of it is perpendicular. So, all right. Okay, enough on that. Let's go back into here. So that was cool. That's just to give you an idea of what this problem's all about. I'll let you do these later. And so, oh, there it is. Oh, there it is. There's the numbers for you. Okay. Oh, whoops. I just answered part D. Sorry, my bad. All right. So let's look at this one. This is tricky. This was a test question once. So I love these types of questions just because they are challenging to think about. The math is really simple on these. So notice there's your resistivity. So now you have to get R equals rho L over A involved. And what is the length of the loop, and et cetera, et cetera. And now you have constant angular acceleration. So you have angular kinematics. This is a great problem because it relates all of those different topics, which means for students, they hate it. Okay. I'm going to leave this one for you to do at home. Give it a shot and see if you can. It's all the pieces are there. You know how to do this. It's all there. All right. These ones are conceptual. Don't spend a lot of time on this problem. But, oh, and here's the other one. But I did make videos. So basically the idea is you could just think about it for a couple of seconds and then watch the video and see what happens, okay? I wrote very detailed solutions trying to explain it. These are very difficult to draw. This solution took me days for this one problem. So literally days. So why don't you guys read it and just humor me and don't spend a lot of time working on it. Ooh, let's try this one, everybody. 30.18. I'm gonna draw it up here on the board. Not spend a lot of time on it, but just a little here. This was a test question once. Just getting it drawn. This is 30.18. Okay, I think everything there. Okay. Oh, and I think I said, so I could say this like that. All right, just reading the problem. This is my take on that problem. I love this stuff, guys. I just do. I don't know why. Something's wrong with me. All right. So we have, this is a rod. Basically, everything else in the circuit has no resistance except for this rod, I think is what I read, right? And there's a connecting wire down here at the bottom. And then there's the other rail going up, but I'm not going to draw that. So just assume it's connected at the bottom. So the loop connects down here. As this thing falls, what direction should current flow? Take a second, discuss with your imaginary neighbor, and think about it. I'll give you a second to get this under control. Okay, any thoughts?
I want to say it doesn't flow anywhere,
Nah.
but I'm probably wrong.
Yep, you're wrong. It's a good thought, though. Why were you thinking that, though? There might be something to that. What were you thinking? Why did you think there was none?
Sorry, I muted myself. Yeah, I'm rethinking it now. A component of it isn't
exactly, and
okay.
so one of the you're absolute. That's the key here. Is one of the components is going to do something, but the other one's not.
The horizontal it's going to be moving anti-parallel. So the vertical component is the only component that's actually affecting, right? The vertical velocity.
Oh, I see. If you want to go that way, okay,
Yeah,
that would be a totally valid approach. So what you're saying is the voltage induced would be something like L times V times B perpendicular, which
right.
you're saying V perpendicular or something. Yeah. That gives us voltage, but that doesn't tell us the current.
Okay.
So let's see what was just thrown in the chat there. Clockwise, curl your finger, then your thumb points to the B field. So let's think. Okay, Jay is on a good idea here. So Jay, kind of unmute here. Let's talk about this. Let's run this through here.
Okay.
Okay, so the loop is down here, right?
Right.
So it's either going to be like this or like that. So this is either going to be into the page or out of the page, right?
I think it's into the page for the rod.
So let's just test this. So there's a proposal into the page, which would actually be an X, right? So if that's I, and let's just put a question mark, this is what I would do. I would guess and check, because there's only two to guess. If it's into the page, which way would current be flowing here? On this stretch, would it be flowing up or down?
Up.
Up.
Okay, so now if that was the case, which way would be the magnetic moment associated with this loop? So remember, this is a loop. It goes into the page, up, and then out like this. What would be the magnetic moment associated with that? Which way would the magnetic moment point? Fly. I feel like Mike Pence.
Down and to the left or up and to the right?
This way. This is the mu, right? Curl your fingers in the direction of the, and this is like the magnetic field created by that. Now think about this. As this falls, mu is essentially the direction of the induced field created by the loop. So a magnetic moment is essentially its induced field direction. Did that make any sense? Let's see. As this thing falls down, does this try to replace the flux that was lost? As it falls down, I lose some magnetic field going this way through the loop. As this goes down, if this was the current direction, this would try to replace the lost flux. This is correct. Did that make sense?
I don't know if this reasoning is correct, but
Try
my
it.
strategy was to rotate the entire problem 90 degrees, so I'm looking down the barrel of the loop, and I treated it like a problem from 30.3, where it's like, okay, well, is the magnetic field going into the page or out of the page? And then I used what we learned there to determine whether or not the current was clockwise or counterclockwise. And then I just translated that back to the original problem and called it a day.
And that's also a good way to think about it.
Okay.
So what, and I think I'm drawing the pictures that described what you just said, right?
Yeah.
Absolutely. So what he's saying is, wait a minute, if I look at this from on end, there'd be a component through the loop with an X. Maybe this isn't all of it, but at least some of it would be an X. And so then if there's this X through there, now it's hard to see that it's angled from this view. So this is not a good way to keep it. So what he did is he flipped it, thought, oh, I'm decreasing the number of X's. That means I need to go this way to create more X's with my induced magnetic field. And then we flip it back to this side, which again gives me the same magnetic moment that I had before. Now here we see, I've been taking it easy on you guys all this time when everything's been at right angles. As soon as you angle stuff, it gets really tricky, because what we see is the induced current does not oppose the flux in the right direction. So it's trying to oppose things, but it can't do a perfect job, and it ends up doing this. Does that make sense? Maybe, más o menos. All right, and so the answer would be, in the end, is it positive k hat or negative k hat?
Negative.
Negative k hat. So if I goes to J, I goes to J goes to K. So this is negative k hat direction. Nice job, Jay, everybody. Was that Corey there too? Nice job. Both of those are good ways to think about it. And I don't know, what do you think? And Nick, here's kind of what Nick was doing, I think, in his mind. What you do is you take a component of the B field parallel and a component, right? You see that? So I think this is where Nick was going. There's a B field that's perpendicular and a B field that's parallel to the loop. Ignore this part because it doesn't matter, because it doesn't go through the loop. It's not a flux. And then it's a little bit easier to see. And maybe that's where he was going. And so if you do this, you're like, oh yeah, it's the same. Is that what you were trying, Nick?
Yeah, yeah.
Absolutely. And so you could also split it up another way. You could also say, well, isn't this rod going down this way? Well, that means there's some component this way and some component this way. Ignore this part, analyze that part. So you either split up the B field into perpendicular and parallel, or split up the velocity into perpendicular and parallel. And what do I mean by that? The induced voltage, you could write it as B perp LV, and you use all of the V, but only some of the B. Or you could write it as E equals all of the B, but only some of the velocity. So you basically take the component, you figure out, and what are we really doing here, right? It's sort of like the magnitude of a cross product, because it's a perpendicular component, which has to do with cross products. Anyways, so, but I just want to point out, you do not do this. You do not say E equals B perp L V perp. That's double counting the perpendicularness, and that would give you too small of an answer for the voltage. Is that good? Now, okay, I need to get back to here. It's getting kind of messy. So hopefully you agree with this. Which way is the magnetic force going to be? Up the plane or down the plane? What do you think? That evil cackle should give you a hint.
It's always going to be up the plane.
Nope.
Nope.
Oh,
It's going to be only in the positive J hat.
I goes to B, goes to J hat. It has a component up the plane because it's magnetic braking, not make you go faster. But that's not all, folks. I go, right, because the force due to magnetism is not ILB. The force due to magnetism is a vector, and it's IL cross B, which in this case, I goes to B goes to straight up, which has a component up the plane, which slows you down. And then it also has a component that lifts you off. Pretty trippy, huh? So I know, yeah. Just be glad this question wasn't on your test for the first time and it's in the workbook instead. That class was miserable. I warned them. I said, I think I might try this. And then, well, that's enough to say about that. All right. It's a good problem. It really forces you to truly understand these things because you can't cheat and just say everything's 90 degrees. That is the real reason this is here. It's here because you can't hide your inability to understand right-hand rules with this problem. And so you can use the conceptual knowledge to a point. However, you also need to know how to do math. And this is the problem that exposes that weakness, where you really understand the concepts, but you can't get the directions of these things. So that was the point of the first two questions, was to force you to think about those two things. All right. Oh man, never enough time. All right. That was a good guess, Claudia. All right. You were on the right track. You had the right-hand rule there. I think you just flipped something. So an easy way to, so imagine you're doing this problem on a test. Think how easy it is to switch this up. What are the ways a sneaky physics teacher could switch this up on a test? Somebody tell me something.
Flip the magnetic field upward instead of to the left.
Yep. So there's that. You could do this. You could do that. There's 4 variations. What else?
Friction.
You could add in friction. What else?
You could connect the rails at the top.
Yeah, you could take this and move it up here. Would that change things? What wouldn't it? It changes some things, but not others, right? Let's see what else we had there. Yeah, but so it turns out this problem, yeah, so like the horizontal, yeah, they all have their pros and cons. All right, so those are the big ways that jump out at me. So what's another way a teacher could mix this up just to be slightly annoying? You could say this is theta instead of that. So all the cosines and sines get flipped, right? I don't know. I'm just thinking out loud. Or maybe what if they gave you this angle up here? You'd have to be like, oh, I know that this is that angle, which means this is 90 minus, right? So those are some different ways you could mix. I'm just thinking out loud. But if you try to go through this one, that'll get you there. I think there's some practice tests out there where I gave you different versions that are already out there in the practice tests. So when you practice, you'll see them. All right, let's do a little bit more here. Let's look at this one. You might not recognize this right away, but remember the other day when we started talking about motors and generators, and I said the women's NBA, which is technically Omega NBA. You remember that? And we had that little generator with the water, and it was, right, there was water pouring out, and then there was a magnet sitting here, and it was on a pinwheel, and it spun around in a circle, and then there was a coil of wire, and there's a light bulb here with a little bulb in it. This is that problem. So I'm going to let you do that on your own. It's not too bad. I'm going to let you read about this part right here, back EMF. So we alluded to this already. I think, I don't know if that was Corey I was talking to or somebody else, but they were saying, what about a motor and a generator? This kind of relates it, but check this out sometime. When you turn on a motor, you put in current and it begins to spin. As it spins, it's a loop of wire spinning near a magnet, or a magnet spinning near a loop of wire. As a result, it acts like an EMF. It's a generator. The induced EMF opposes the motion. It's magnetic braking, not magnetic make you go faster. And so as a result, the net effect is to create a voltage inside, an EMF inside, that opposes the current flow. As the motor picks up speed, this voltage gets larger, and it's called back EMF. Eventually, the back EMF is a major factor in limiting the speeds of motors. If you turn on a fan, why doesn't it get faster forever? You're applying more and more torque, but eventually the back EMF just gets so large, it opposes the current and you can't get any more torque. These are some practical applications. We talked about that last time. Transformers. We'll talk about this and then we'll take our break. I know I'm flying here, but I'll be honest with you people, this transformer stuff is not going to be on your tests, okay? It's not on your quiz, it's not on your final, but if you are an electrical engineer, I think you'd be crazy not to read this. The idea here is, we showed a simulation of this last time, but here's the problem that it relates to. If you want to see that simulation again, I'll put it in the chat later. But the idea is this walks you through the information. So if you're a physicist or an electrical engineer or anybody that thinks you might need to understand transformers, read this problem, have the solution open. Do not try to work through it without the solution. That way you get through it as fast as possible. You get exposed to some of these words. Here's some typical things here. And then this problem right here, you could try to understand why you use transformers. Go for it, Rye. What's up?
Oh, I was just wondering, does that include exemption from oral exam final
Yes.
also?
Yes.
Any conceptual questions? Okay.
Yeah. So page 20 and 21, or problem 30.20 and 30.21 are really interesting. They're really useful to understanding electrical engineering problems and physics problems, especially this one. If you've ever wondered, why do we use AC power when it can kill people more easily than DC power? It's because it's cheaper for the power companies, right? This is the way life is. A little bit of death is worth some money to them. Same thing with why they, the power companies are starting fires all over. It's cost death trade-off, right? Same thing with coronavirus. You can't just have the world be completely closed down all the time. There's got to be something. So it's a very challenging problem when you have to face money versus deaths. How much is a human life worth? That said, this page, in theory, could give you a tiny inkling of why a power company might choose to make a riskier design that uses AC power and is more likely to kill humans than to use DC. All right. So I'm glossing over that because it's not on your test. Woo! I think we're ready for the break. Oh, sweet. We're not going into the next chapter. I think this is still chapter 30. RL transients. Let's make sure. Yeah, this is still chapter 30. So next up, right after the break, we're going to start talking about inductors and circuits. So I know I sped up there rapidly. Yeah, I was trying to get through that stuff from the bottom of page 184 to the bottom of page 185, not on your final, not on your oral exam, not on your quiz, not on anything, but pretty interesting. Sorry, I had to gloss through it. You got to cut your losses somewhere. Okay, let's take a quick break. We'll come back at 5:50 and then we'll hit it, unless anybody has any questions. Super interesting stuff, people. I just love this stuff. Super fun. All right, go ahead, take your break, and we'll see you at 5:50. We'll talk about inductors. Just getting some last simulations ready, okay?
When do we start learning about the flux capacitor?
Oh, that'll be soon. Don't you worry. Doesn't that sentence annoy you now that you know what flux is and a capacitor
Yes,
is?
yes, it does.
But that's all right. That's the curse of knowing science. Let's stick it there. All right. All right. Oof. Okay. So I think we're ready to go here. Let's see.
But now I do understand how big a gigawatt is.
Yeah, right. All right. So I want to talk about inductors. So maybe I'll start very briefly with the simplest possible inductor I can think of. All right. Let's get into this. Okay. Oops. You guys could talk politics after class. That's cool. Let's just focus on, that's my fault for bringing up death in the power company. All right. So, all right, let's focus on what we got to get done here. And then it's only,
Oh no, I'm just mentioning how the electoral college works.
oh, I know.
I
Yeah.
just
Okay.
think it's weird.
It is. So let's get to it. It's not that we can't talk about that stuff, but we got to get this lecture done just because.
Short amount of time.
Yeah, right. So I want to talk about, forget the book for a second. Forget everything. Watch the screen, all right? Let's start super simple. A circuit that has a resistor and a switch. Now, okay. In this case, when I close, right now there's no current. I think you all agree with that, right? When I close the switch, most of you probably think there's going to be some current. And you'd probably think that value would be E over R. The way I'm phrasing it implies that's not the whole story. In fact, when you close the switch, there's no current. It's not a dead battery. A little bit after you close the switch, this is the correct value of current. Explain why.
Needs to reach the resistor?
What's that? No.
Okay.
Okay, so
it would be...
you're talking about the time. It turns out information about electrical signals will propagate at the speed of light. So unless this is millions of light years long, that's not significant. In fact, it would be on the order of nanoseconds for that information about, once you close this, the electric field is registered nearly instantaneously. Technically, there is a slight retardation there. And so that's the physics term, the retarded potential. But that's not what we're talking about now. So that it turns out that is slightly true. There is some time lag, but that's negligible compared to what this other factor is.
Does it have something to do with the fact that when you immediately close the switch, there's like a spark or something?
Okay, usually that's not true. That's when you open the switch. I don't know if you've ever taken a vacuum cleaner, it doesn't spark when you plug it in, but it does spark when you pull it out and it's still running. Same with a fan. What do you mean, Alexis? I just don't know. Explain.
I thought that when you allow the current to run, all of a sudden you generate a magnetic field through that loop you made.
Which way? In this
Um,
case, if let's say current did flow this way,
into the page.
so wait a second. You mean the very act of turning on the circuit creates an external field, and then the circuit itself opposes its own motion? Opposes the, you are correct. That is what's happening here. Effectively, this is what happens. When you turn on the circuit, current would try to flow this way. If current was able to flow that way, it would create a magnetic field into the page. Well, that means you've created a change in flux through a loop. That means the loop itself would say, no, I'm going to create a voltage that opposes that change, which doesn't allow current to flow. And actually, this is exactly what happens. Now, it turns out, remember this, the induced EMF is minus N d phi dt. And so what happens here is it ends up being a compromise where initially it says, thou shalt not pass. And then it says, yeah, you're not changing that much. I'll deal with it. And it starts to allow more and more current to flow. And eventually it asymptotically reaches this value. This is a property of every circuit, everywhere. Think about it. You plug in a fan, it's not just instantly. A fan has many loops of wire. The induced EMF for something like a fan or a vacuum cleaner or anything with a motor in it, all motors have a lot of coils, a lot of N. You get a lot of back EMF. This is essentially a back EMF. When you close the circuit, it opposes itself and then it releases and lets the current flow. Questions about that concept?
So I'm assuming, like, since it's dt, like, we could obviously calculate the rate at which it is giving that off. Like,
so in general, what you do is you could calculate the flux. If you know the time, the average EMF is equal to the change in flux over change in time. I don't know if this is on a quiz or on your final, but it's on one of them somewhere. So you may want to write down that the average EMF is delta. So in theory, if you know approximately how long it takes for the motor to get up to speed or whatever, that gives you an idea. And if you know the change in flux, you could get this voltage, etc. Is that good?
Yep, thank you.
Yeah. So I guess you could say it's approximately equal to. So this is the standard. And I'm telling you, it's on one of your questions. I don't know if it's the quiz 30 or if it's in the final exam. It's somewhere, I think. Oh, what did I forget? There's an N. Obviously, the number of loops matters, right? So if you did 2 loops here, so this is why things like motors and things have these problems starting, right? There's this massive back EMF once you try to get it going. Now, in practice, what do? Right? Think about this. I don't know if you remember this at all, but remember when we had batteries? Batteries have a bunch of stuff in them. Well, what we were doing is we could say you could model that as an ideal battery plus a resistor. Well, you could take any circuit in the world and model it like this. So we know that every circuit tends to oppose itself. So what we do is we say an ideal circuit, you could still have an ideal battery. Let's assume battery resistance is negligible right now, right? What you do is you have a new symbol, right? The inductor. It looks like a coil of wire. Why? Because we know coils of wire oppose themselves strongly. So what you do is you ignore this weird, hard to quantify effect. And what we do is we can quantify it with a property called L, inductance. So L is inductance. Inductance. Sometimes it's called self-inductance. So it's a measure of a coil's ability to resist its own changes to current. Okay? And so this is a new thing called an inductor. So self-inductance is L. The inductor is the object. Inductor is the object. Inductance is the number associated with that object. It's measured in Henrys, or capital H.
What was that full sentence? A measure of ability to resist what?
Oh, okay. I'll do it again. Inductors are a measure of something's ability to resist changes in current. If you try to change the current, inductors oppose that. That sounds vaguely familiar. What did capacitors oppose?
Voltage?
No, close. Not voltage, but related to voltage.
Change in voltage.
Changes in voltage.
Jinx, Ryan. I jinxed you again, dude.
You know what I'm saying? Yeah.
Dang, Travis. Dang.
Jinx-o-matic.
That's the
All
only
right.
way I can laugh right now because I'm tired.
Oh yeah, I'm sorry, guys. I'm like super excited and having a blast here, but it's like you guys are bored. Don't worry, I'm getting to the demos soon. The demos, the simulations. All right, so here's the deal. Capacitors oppose changes in voltage. Again, they oppose changes in voltage. You see the difference there, Tom? Just trying to be technical there.
Yeah, I appreciate it.
Yeah. And then inductors do not oppose current. They oppose changes in current. So here's the thing. Once a circuit gets up and running and the current is flowing, it's basically like the inductor is just a wire that's not even doing anything. However, right when you close the switch, it acts like an infinitely large resistance. It's almost like, let's do a quick comparison here. Because if you already know a little about capacitors, let's see what's the same and different. Let's say we had an RC transient. Okay, and there's a switch. And let's say I close the switch, and this is t equals 0 minus. Here's t, 0 plus. T equals infinity. Give me a second. Okay. Now, at t equals 0 minus, if this is an uncharged capacitor, how much does it impede current flow?
Not at all, right?
So it looks like a short or a break. Does it look like a short circuit, just a connected wire, or does it look like an open circuit?
Short.
A short. The cap looks like a short. So if it's initially uncharged, you close the switch, it acts like a short. How much current flows? E over R. You know what I'm saying? Now let's go to long time. The capacitor is charged. What happens when it's fully charged? How much current flows?
None.
And so does this look like a short circuit or a break in the circuit?
A break.
A break. Now let's do the same thing with an inductor. Okay. And then before I do that, I just want to say here, what does a capacitor preserve?
Charge?
Nope. Oh, well, that's related to it. Q equals
voltage times
Yes.
capacitance.
So do you agree when you say it preserves its charge, that's also the same analogous to preserving its voltage?
Right.
Yeah, and so the term that you'll hear electrical engineers saying all the time is I say, oh, well, a capacitor preserves its voltage. That means the voltage doesn't change from the 0 minus to the 0 plus. So a capacitor preserves its voltage. So that's our review of the RC transient. Let's hit this now down here. Help me out now. When you try to close this circuit, the inductor says, I refuse. How much current flows?
None.
None. So right now, does this inductor look like a short or a break? An open circuit or a short circuit?
A break.
A break. Okay. So take a guess what it looks like after a long period of time. After it's been going a long period of time, it eventually reaches some sort of equilibrium, or the word in circuits is steady state, meaning things not changing. If things aren't changing, the flux isn't changing, there's no induced voltage. What does the inductor look like after a long period of time? Short or a break?
A short.
A short. And so notice this interesting behavior. They behave exactly opposite. When we get to AC circuits, we'll find out one of these is equivalent to taking a derivative and one of them is equivalent to integrating. And that's literally what some electrical engineers might call. Just put in an integrator. Oh, just take a derivative. Stick in a capacitor or an inductor as appropriate. More on that in a later. Okay. You could do calculus with circuits. All right. Like literally just put in a waveform and stick in the right symbol and measure the right voltage and you get the integral of the curve or the derivative of the curve. It's amazing. All right. Anyways, in this case, I was equal to 0, right? And so how much current flows here in this circuit? E over R. Yep. So let's pause and see if that makes any sense at all. When we did RC transients, what was important? We need to know the initial voltage here. And then what we do is we'd go through the circuit and say, well, I know the capacitor preserves its voltage from 0 minus to 0 plus. I figure out the initial state, the final state, and then I can write the voltage or the current on anything. And if I needed to get the power, I would take the current and square it times R. If I needed the energy, I could get the voltage times the charge, but I can't use my shortcut trick to do power or energy because they're second order terms. There's a squared in them. So yeah. Now, what would be the equivalent statement down here? What does the inductor preserve from 0 minus to 0 plus? What's the equivalent statement? Inductor preserves what?
The current.
The current, right? It was initially no current. It keeps that current locked because it doesn't like changes in magnetic fields. Magnetic fields are caused by currents. So inductors oppose current changes. Okay, capacitors relate to electric fields. Oh, we're getting close, people. Oh my gosh. It's getting cooler. To me. All right. Now, there's one more piece of the analogy here. We say a capacitor is charged. The correct term for an inductor is not energized or energized. Well, why would we use that term? What type of energy is stored in an inductor? Magnetic energy. More on that in the next something. I'll just keep saying that and lie to you, and then we'll never get to it, right? But no, basically, here's the full story. Capacitors preserve voltage. They store energy in the electric fields between the two plates. Inductors store energy in the magnetic fields inside the coils. So this is a magnetic energy. This is an electrical energy. And so this stores electrical potential energy. This stores magnetic potential energy. If you try to turn this off, there's so much electrical energy stored in there. The inductor says, thou shalt not turn off. And it makes a big spark when you try to pull the plug out of the wall. What do you think? Pretty fun, huh? Let's see how you do with these simulations now. Unless there's questions. I just love this stuff. All right, let's take a look. I think I have 4 circuit simulations here. I want you to tell me what should happen in each one of these if I do it right. Let me see if I get them in the right order. All right. Here's a circuit. Hopefully you could see that. Now, if let me see, can I get rid of those electrons? I don't know, whatever. Let's not, there we go. All right, and if we want, we could make this a schematic. All right, so let's do it this way. Oh, let's put those electrons back. All right, so just so you can see it without the electrons, there it is. And to be clear, I just want to be clear, this light bulb is like a resistor, okay? All right. So now let's put those electrons back in there. Right now, I'm going to keep this switch over here open. Currently, how much current is flowing in this circuit?
I'd say none.
None. So what is the term that we would use to describe the solenoid, excuse me, the inductor? You're probably going to hear me say this. I don't know if you recognize this. This is a solenoid, a big long coil of wire. Solenoids make excellent inductors. So do toroids. So if you hear me accidentally say solenoid or inductor, I mean the same thing. The inductor is a solenoid in this particular case. What's the correct term? So now going back to here, what is the correct term for the solenoid? Do we say it's charged? Not charged? What do we say?
Not energized.
Not energized. So just trying to hammer that home. So now when I close this circuit, the second I close it, how much current should flow?
All of it? None
Remember, of it. Inductors oppose changes in
current.
And so an inductor preserves its current. Currently, or at this instant in time, what is the current?
No.
0.
So when I close it, it will still be 0. So, and then eventually, now remember, because this switch is open, we don't have to worry about this. I could even do this, split this junction. Just to be clear, this loop over here on the right has nothing to do with the circuit right now, okay? So in this case, when I close it, no current flow, right? Wait for it. Ooh, there it goes. Now, wait a minute. Is current flowing the wrong way in this simulation or no?
No.
Well, no. Electrons, right?
Yes. So the electrons, you know me, I love to focus on that. The current is flowing this way. Electrons move this way. All right. That's good enough of there. All right. Next. What should happen when I try to open this circuit?
It should want to keep flowing for a while.
Okay, and so let's see what happens. This is where we don't have the good math for it. And so in this case, the simulation will just turn off, but there's actually a finite amount of time, and this is when you would normally get a spark up here at the switch. So now here we get something kind of crazy. Let's see if we can, oh my gosh. If I want to make this go faster, how do you think I could make this approach speed faster? How could I make this light up faster?
Use a smaller inductor.
Smaller inductor. So let's see. If it's a smaller inductor, it will oppose changes in current less. So let's see if we could do that. So right now it's 50 henries. Let's just go down to 10. All right, so let's try this out. It turns off. Let's try, notice the switch, an open switch is infinite. So let's see if that goes a little faster. Nice job, Trey. All right, so now what I want to do, I need to split this.
So is there an obvious reason that I'm just like not seeing as to why the current goes back to 0? So like the current obviously spikes and then.
It's because it's very difficult to see with this simulation. Normally what happens is as you open the switch, the resistance does not go to infinity instantly. The small air gap will actually be a large resistor. And what happens is the current actually rapidly goes to zero. So I'm going to try and set this up a slightly different way. Just give me a second here. Let's do it like this. So I'm going to set this up like this. Wait, I want this one to be, sorry. I set all these ones up and I forgot about this fact right here. So let's go here, we'll go here, and I'll put the light bulb up here. And you know how these circuits are. If you change one little thing, it can be a significant change. So now my light bulb's up there. And, ooh, I want this. I need this to go to here. I think, wait, let me think. All right, whatever. Let's see if this works. So now, okay, we got our light bulb up to speed. So now what I'm going to do is I'm going to close this switch and see what happens. In this case, we see that the inductor is storing the energy and it's released. So it's a little bit tricky to design. You really need a sweeping switch, and I'll try and show you that later. But the idea here is what you could do is you could store energy in the inductor by energizing it. We let it get up to speed. Now that it's up to speed, the inductor has a lot of energy in it, right? There's a lot of current flowing through those coils of wire. And so let's say it's probably creating a large magnetic field this way. And so if I try to turn it off, that magnetic field would rapidly drop to zero. And so if it does that, there's energy that could be released. So what we do is if I could do this infinitely fast, what we do is we'd switch this up and close this down. Oh, but I can't do it. If I could switch those at the same time, you would see all the energy goes over to the other bulb. And so inductors are, you see why we cover this later in the, yeah. Let's move on to the next one and see. Hold on. All right, so we got this situation right here. So in this case, I'm going to close the switch, all right? Now I want you to think about what should happen to the current in the inductor or the light bulb. In particular, what should be happening, and maybe we could get the voltage out here too. So I'll do this voltage across the light bulb. And so, yeah, let's do this. So in this case, if I want to analyze what's happening, let's do a voltage chart too. I'm going to talk about the voltage across this and the current through this, and then this DMM will also get the voltage across the light bulb. So when I close this switch, right now, how much current through the inductor? None. How much will be there afterwards? After a long time.
An infinite amount?
Yeah, let's find out. So how about through the light bulb? So when I close this switch, the inductor acts like a brake. Where does all the current have to go?
Through the light bulb initially.
Right. After a long period of time, the inductor acts like a short. Where does all the current flow?
Through the inductor.
Yeah, and so we should see the inductor light on fire. Let's see if this makes sense. So watch what happens to the voltage of these things. Ooh, what should be true? I just want to point out, you guys just told me that I is equal to 0 at time t equals 0 plus, right? Right through this one. So in this case, what's the voltage across the inductor? Is the voltage going to equal 0?
Right? I think so.
It would be 9 using KVL. 9 volts. Why? Think about it. If I do this loop, if I go around this way, right? I know that the total voltage has to add it to 0. So I expect 9 volts. So we expect it should peak out right here, something like this, right? Depending on the polarity, it'll either be plus or minus. All right, let's clear all those. So let's see what we see here. All right. And so when I run this thing, here we go. The light bulb is bright. The inductor is blocking all the current flow. However, and notice the voltage across the inductor is very large right now, right? It's almost 10 volts. So now as time goes on, there's, yeah, let's restart that. Oh, there's your discharge. Let me change this so it's faster. All right. So in this case, all right, come on. Let's discharge it. All right. So again, we should use energize, but whatever. All right. So what I'm going to do, watch this again. I'm going to close this. The inductor opposes current, but the resistor does not. So the voltage. Okay. So now once we get this going, these are all in parallel with the battery. If this is 9 volts, this is in parallel. This should be 9 volts, right? This is in parallel. This should be 9 volts. Everything's or by KVL. So now what I'm going to do is when I open the switch, oh, look at that. Look at that. Oh, there goes the, okay. So it does eventually light on fire if we let it go long enough, right? But now when I open this, did you see that voltage change? Look at the voltage on the light bulb. It's much bigger than 9. Is that a mess up? What do you think? Let's put this back in. Let's get this thing up to speed here. Sorry, it takes a second. What do you guys think about that? Do you think that's a artifact of the simulation or not? Based on the way I'm talking. Here we go.
I don't think so, no.
Yeah, it's not an artifact. So what's really crazy about this is inductors. This is why it's powerful enough to spark. Once you get it up to speed, if I open this, watch the voltage across the light bulb and across the inductor. Ready? Here we go. Oh, the voltage across that inductor is huge when you change it, because turning off a switch is like changing it infinitely fast. So you get this massive change. All right, we'll get to the math in a second, but that's an interesting phenomenon. All right, maybe we should do some math really quick. All right, let me show you the other ones here. Here's an interesting one. You can think about this. When I get this thing running, let's get this. Let's change these to, sorry, I forgot to change the values.
This is already looking like the capacitor ladder where it flips over
Exactly. Time. Oops. How do I change inductance? There we go. It's exactly the same as the capacitor where the concepts flip, right? So when I close this one, inductors oppose current. So initially, watch the inductors. There should be no current initially in the inductors. And then rapidly it starts to build up. And then eventually there's going to be a steady state. What do you think? Is this going to light on fire or not? Over time.
Yeah, I would say so.
These become shorts. The current is going to flow like this. Look at those resistors. Do you see them? How much current is flowing through the resistors at this point? Almost none. And that makes sense because they're short-circuited by the inductors. So we see that you have to be really careful in the real world dealing with inductors. I swear we're going to get to math at some point. Just give me a second. All right, so that's going to light on fire any second. So let's stop this one. And I had one more. This one. Whew. Oh, you guys are going to hate this one. All right. Let me clear my drawings. This is one of my favorites. It's extremely confusing. Okay, when I close this switch, what should happen? How much current should flow initially?
None.
None. How much voltage will be across the resistors initially? If there's no current initially, how much voltage across each of the resistors?
None.
None, because of Ohm's law. Therefore, how much voltage is across each inductor?
None.
Nope.
Damn.
It's KVL. Go around the loop. There's volts E over here. How many volts does the inductor have to have?
E.
E. Otherwise, you don't have conservation of energy in a circuit. So remember that inductors can have voltage even when there's no current. They are not like resistors. They do not obey Ohm's law. In fact, the voltage across an inductor is related to negative L di dt. It's related to changes in current. We know that when the current changes, you get a voltage, right? And this is the equation. So this is actually the equation for self-inductance. More on that in a minute. I'm trying to get you the conceptual knowledge here, right? Sorry, annotating in Zoom stinks. Okay. All right. So I think that's everything we need to know here. All right. So now I'm going to let this run for a long time and let's see if you're right. No current flows. And then it rapidly says, all right, I'll let some current flow. It starts getting used to the idea. This is the second time today I've tried to what's that word? Help me out. Anthropomorphize. I can't say it at all on ever. What's that word? Anthropomorphize. Oh my gosh. Can anybody help me out?
Anthropomorphize?
Yes, that one. Anthropomorphizing. I don't know. I'd have to look it up.
The inductors are people.
Yeah, exactly. Attributing human elements to them. You can tell how much I really care, but I'm not saying that right, but it's that word that looks like that one in the chat, but that's not right. Thank you. Anthropomorphize. Thank you. Right on, Nate Dogg. All right. So in this case, what's going to happen when I open this? Let's clear my drawings and talk about this. You guys are going to hate this. All right. Which way is current flowing in this inductor right here?
Down.
Down. There's a current here. How about the current in this one over here?
Same.
I. So now, what's going to happen when I open the switch? What do inductors like to preserve?
Current.
Current. So this one says, now check this out. If I open this switch, none of this is in the loop. When I open that switch, what should happen? Inductors preserve their current, right?
So like a black hole opens and everyone dies, or what?
Let's find out. The current just goes off because the two currents persist, but one's flowing clockwise, one's flowing counterclockwise, and they instantaneously cancel out. Bah! My life is horrible. Isn't this amazing? Surely I wouldn't do that to you, would I?
So the field just immediately disappears?
Yeah, within a time scale on
Or,
the
yeah,
order
not
of the speed
immediately,
of
but-
light. My child just told me to turn the volume down. All right, whatever.
Feels like adding a flywheel and giving the current some inertia or something. It's very weird.
Yeah. So it turns out, I would say it this way. Take a circuits class. I will avoid giving this problem on a test. So anyways, let's maybe look at one problem. We got 5 minutes, but I just want to show you this one here. This is kind of all that. So getting back to what we're actually supposed to do, the concepts of inductors are not obvious. I hope you realize that from all these examples. That's where I was trying to go with this. Apologies if I did a bad job. However, we can use the same equation as before, only look at this. Our time constant is now inductance over resistance. Think about it. The bigger the resistance, the smaller the current, the less big of a deal this is. So that's why R is now in the basement. Whereas over here, inductance, the more turns you have, the more inductance you have, the more significant this will resist changes. So if you have a big L, you resist changes. If you have a small R, that would create a huge current. That would be a huge problem. So this time scale is now L over R. All right. And again, this is not valid for energy or power. So let's take a look at this one. Let's determine the current in the inductor for this problem. Okay, you've got this. So I'm going to look at 30.22. So I don't know if that was the right decision to do all those demos. I hope so, because I just don't know. But let's do at least one problem and get you out of here. We'll probably have to do at least one more next week too. But I think we're doing all right. Where was it? Oops, I switched the order. The voltage across the inductor is 0 initially. Now we go over to T equals 0 plus. We close the switch. Okay, what does the inductor preserve? Help me out.
Current.
Yep, inductor preserves current. What does it oppose? What is it?
Magnetic field. Okay.
Okay, true. How does it relate to current? It opposes
Change in current.
changes in current. Good.
Thank you. Sorry.
Yep, changes in current, or changes in magnetic field. You're right. Okay, good. They're related. Usually the B field is some number times I, right? So you're right. Okay, so in this case, what does that tell us? Oh, wait. Which one of these things do I want to bring over? What does the inductor preserve?
Current.
Current. So what do I bring over?
Current.
Current. I equals 0. What does that tell us? Once you know this, what is next? What can you get from no current?
The voltage,
Across
the resistor,
equals
0.
0.
Yep, because I is 0. Okay, so what does that tell us now? What's next? What else can we learn?
Well, if the voltage is 0 across the resistor, it has to equal E, or whatever we call voltage across the, would we say across the inductor?
Yep.
Okay.
It's always voltage across, current through. So that would be the other thing. There we go. We're off to the races. Next. This is T equals infinity. After a long time, what was the trick? After a long time, what do we know about this? Inductor acts like short or a break?
Short.
Short. Okay. If it acts like a short, how much voltage is that? Or, well, I don't know. What does that tell you? I don't know.
That the current is max through the whole thing.
Yeah, good way to start. So what does that tell us? What does that tell us about the voltage?
The voltage is E.
Mm-hmm. So what does that tell us about this voltage?
0.
Yep, by KVL. So now, what's the current as a function of time? I final plus I initial minus I final times e to the negative t over tau. What's I initial and I final in this case?
I initial is 0 and I final is E over R.
I should be doing that in red, shouldn't I? All right.
It's all right. Bobby can't see it anyways.
That's right. Sorry, Bob. Hello, Bobby. Can I call you Bob? I had a teacher named James Glazebrook, and he used to call me Bob. Well, Bob, it's not whether or not I know what I'm doing. It's whether or not you know what you're doing, Bob. That's what he said to me in the middle of a class one time.
It's a true story.
Oh, yeah. I said,
Oh my gosh.
it was a logarithm A minus B. I still remember this day because it was log A, and he wrote log A times B. And I went up to him after class. I'm like, excuse me, was that supposed to be log A over B? He's like, the question's not what I... Yeah, anyways. He's all right guy. I liked him, actually. My dad's name, everybody called him Bob. So, sorry, Bobby. I might call you Bob. All right, anyways. All right. So notice, what type of this? Is this exponential decay or asymptotic rise?
The rise.
Yes. So this would be E over R times 1 minus e to the negative t over tau. And so that's the asymptotic rise. And what is tau? Tau is this new thing, L over R. And in theory, you could now do this whole chapter. Maybe. Let me see. Let me see. Come on now. Yes, thank God. This is the last topic in this chapter. So we'll do a couple more problems out of this stuff next time and then move on. And actually, because Monday you have a quiz, right? So Monday you have a quiz, and then we need to finish this stuff Monday night, and that'll be a good spot. And then we'll pick up after the holiday on Wednesday with the new material out of chapter 31, I think. We'll see. I may get into chapter 31 next time, but so far so good. Maybe-ish.
Yep.
Yeah, and so hopefully we did a really good job on RC, fingers crossed, and this will not be as bad as it looks. All the same tricks work, and that was the advantage of teaching it that way, so that we could have a little easier time now, I hope.